the Euler characteristic, or so to say the Euler number. So this is the definition of this Euler number or Euler characteristic. So definition of Euler characteristic. Let X be a topological space. Let X be a topological space that is homeomorphic to some polyhedron. Topological space that is homeomorphic to a polyhedron. Let's call that polyhedron as K. Then the Euler characteristic is denoted by psi of, in fact it's called a chi, chi, chi of X is given by chi of X is equals to number of vertices in K. This is the number of vertices that we denote with V, minus the number of edges plus the number of faces of that polyhedron. So V is vertices of K, E is edges of K, and F is faces of K. And now what we want to do, we want to see how we can compute the Euler characteristics of some polyhedra. So let's now start with an example. Example 1. Let's try to compute the Euler characteristic of a point. Very simple thing. So a point doesn't have any face. It doesn't have any edge, right? The point itself is just a vertex. So what will this be? B minus E plus F. There is only one vertex with 0 edges with 0 faces. So this is just 1, right? Done. Then let's try to compute the Euler characteristic of a line. In this line there is one edge and two vertices. So let's say this is our vertices and this is our edges. So again, using this formula or relation, whatever you want to call them, you see that you have two vertices, you have one edge, and you have 0 face, right? So this is what? Again, this is 1. Now if you recall that a few moments ago we said that if two spaces had the same topological invariant, that really doesn't mean they have to be necessarily homeomorphic to each other. And this is that example. You see that there is no continuous deformation that takes a point to a line or a line to a point, and yet they share the same topological invariant. However, if two spaces are homeomorphic to each other, then their topological invariants would be the same. That's guaranteed, but the converse is not necessarily true. Okay. Now let's move on to some more examples. Let's say this is example 3, and we want to compute the Euler characteristic of a hollow triangle, or so to say a triangle with 3 arms or edges only. It doesn't have any face. So you can think that there are 3 rods, and you are using those 3 rods to make a triangle. There is nothing over here where the cursor is hovering. Okay. So if you want to compute that, we again write the relation you see that there are 3 vertices, right? So 3 vertices, and we have 1, 2, 3 edges, right? And 0 face. So this is what? 0. And let's take another example. Example 4. Here we want to compute the Euler characteristic of a solid triangle. This time the triangle is filled in. Okay. So again, you see there are 1, 2, 3 vertices. So vertex would be 3. There would be 3 edges. But now since this is filled in, it's a 2-dimensional surface, so there will be 1 face. So face is equals to 1. So our Euler characteristic for this solid triangle is just 3 minus 3 plus 1. This is just 1. So this immediately tells you that this hollow triangle is not homeomorphic to a solid triangle. And you can intuitively understand very easily why is that. Because a hollow triangle doesn't have any face. The space in between these edges is not filled in, and there is no such continuous transformation that can make the whole filled up, right? So this is one way to understand it as well. Now if you want to compute, let's say this is I think this is example 5. Yeah, the Euler characteristic of a square. This is a hollow square. You see you have 4 vertices, you have 4 edges, and with a 0 face. So you can have the Euler characteristic as 0. Similarly, if you take a filled in rectangle like this is just 1. Now these are pretty simple geometrical objects. Let's try to focus on something else.